Hi, today we're looking at 3.1 and 3.2 exponentials and logarithmic functions and their graphs. So let's review a couple of things. In this unit, it's basically what we learned in Algebra 2, but we're just kind of going back over it. We use logs and exponents along calculus, so it's kind of important to make sure we've got the information. We've studied polynomials and rational functions, which we can express in terms of algebra operations, such as addition, subtraction, multiplication, raising to a power, extracting a root. A function that cannot be expressed in one of these ways is called a transcendental function. Some examples of transcendental functions are the log functions, exponential functions, sine, cosine, which we're going to learn shortly. Examples of transcendental numbers are non-algebra numbers, so that's where we use like pi and e to represent other numbers. So exponential functions, the definition is f of x equals a to the x. A has to be greater than 0 and a can't be 1. We have learned some different formulas. We've talked about investment formulas, compound interest, where we take and divide the rate by the number of times during the year it's compounded, and we multiply the power by that same compounding period. We've talked about continuous compounding. Sometimes teachers refer to that as the PERT formula. And we talked about some of the most common compounding periods are quarterly, meaning you calculate it every 3 months. Monthly, meaning you calculate it every month. So that might be something like buying a car, something like that. Or daily, once every day. Compounded continuously is every minute of every second of every hour of every day. So there's a little bit of difference there. Then let's review some of the log rules. So we have natural log base a of 1 equals 0, which is the same thing as ln of 0. We have log base a of a equals 1, which is the same thing as log of e is 1 because the base here is e as well. We have log base a of a to a power, which leaves us with the power of x. Same thing is true here. When it's natural log base e of e to the x, we get x. And then if we have a base that has a log in the exponent, if the base of the log and the base of the exponent are the same, then that equals x. So that's true here. So this is the log bases, and these are the equivalent ln bases. We learned that if log base a of x equals log base a of y, then for the property of equality, x has to equal y. And we learned in the natural log form, ln x equals ln y, then x has to equal y because the bases here would be the same. They're both e. So looking at our notes, we had a table that we calculated, and you would just put in the values or evaluate the values from 2 to the x and 4 to the x. So f of x is 2 to the x, so when I make the exponent negative 3, that becomes the fraction 1/8. When I make the exponent negative 2, that becomes the fraction 1/4. When I make it negative 1, that becomes 1/2, and then when the powers are positive, you get your whole numbers. So those are just the same patterns here again, 4 to the power of 3. If we look at the graph, 2 to the x, we know that we have our parent function points that happen at 0, 1, and 1, 2. We know we have a horizontal asymptote at y equals 0. We know that when we graph this function, you need 3 things on the graph. You need the horizontal asymptote, you need those 2 parent function points, and then the curve that goes through it. So in this case, the domain would be all real numbers, negative infinity to positive infinity. The range would not include the horizontal asymptote and go from 0 to infinity. There are no x-intercepts. There is a y-intercept at 0, 1. There are no zeros, and we said the horizontal asymptote is at y equals 0, and this is considered an increasing function because if you start at the left side of the graph and read across your graph left to right, the y values continually get bigger. The graph of 4 to the x looks something like this, and it's a parent function. Notice it's the same thing, 2 points here, 0, 1, 1, 4. These are the 2 x values we use to make our parent function points, 0 and 1. And then the horizontal asymptote is still y equals 0 because it hasn't moved up or down to shift it off that horizontal axis. So we have the horizontal axis, the point at 0, 1, the point at 1, 4, the curve that goes through them. So notice over here, nothing's changed. It's still negative infinity to positive infinity for the domain. It's still 0 to infinity, not including 0 for the range. There's still no x-intercept. There's still a y-intercept at 0, 1. There are no zeros, horizontal asymptote, and increasing. So all of the exponential parent functions, because there could be an infinite number of them, anything that's just in the form of a base number to the power of x could be considered a parent function, should all have similar characteristics. Then we looked at some negative exponents. So remember that if you have a negative exponent, that brings it to the bottom of the fraction. So then this would become 1 over 2 to the x, when this would become 1 over 4 to the x. So when I have a negative exponent and the value I'm plugging in is negative, then we have actually a positive exponent, so it becomes the whole number 8. So you have to watch out for the negative powers there. We graphed these two just like we did the first two. And so sometimes in Algebra 2 they'll have you do 3 points. So I went ahead and did this set with 3 points. I'm fine with 2, but a lot of people will do 1 and -1 so that they have a point on each side of the y-axis. So that's really up to you and what you're comfortable with from Algebra 2. So in this case, my parent function points are -1, 2, 0, 1/2, and I'm sorry, -1, 2, 0, 1, and 1, 1/2. And then we have our horizontal asymptote. So notice that none of this has changed except what the function is doing. And that's because if I read it left to right and I move across my graph this way, all of the y values are getting smaller. And they're always going to continue to get smaller, even though here it just gets smaller by smaller amounts. So it looks a little more flat out to the side. The same thing I did with 4 to the -1x. So you could see how that graph curves. Feel free at any point to stop the video and take a longer minute on a problem or a graph if you want to look at it again as I'm going through the notes. Here's all of the information we talked about. Compounding interest. The A is the final amount, the P is the principal amount or the starting amount, R is the rate as a decimal, T is time in years, and N is the number of times compounded quarterly. So if you're doing, times compounded in a year. So if you're doing it quarterly, that's 4 times a year. If you're doing monthly, that's 12 times a year. If you're doing it daily, that's 365 days a year. And then when we look at the compounding continuous, very similar designation. A is the final amount, P is the principal amount, R is the rate as a decimal, T is the time per year, but it's compounded every second of every minute of every hour of every day. So if we look at problem 2 on the note page, we have a principal of 3,000, a rate of 6%, and we want to find the value after 10 years. So if I compound it quarterly, that means my N is going to be 4. So I take my principal, which is 3,000, 1 plus the rate as a decimal, which is 0.06. So 6% changes to 0.06. Then I divide it by 4 because that's my compounding time. And then I multiply the power by 4. So I can put this in a calculator and evaluate it, and I get $5,442.60. Okay, so then I just calculate again monthly, change the 4 to a 12. I get a little bit higher amount. Change it to daily. I change the 12 to a 365. I get a little bit higher amount. So this is what it is daily. If I use the compounding continuous formula, that's the PERT. So the principal is 3,000. The rate is 0.06. The percentage is a decimal. And the time is 10 years. And so in this case, it comes out to be pretty much the same because of the way I round off at 2 decimal places to get my money. So it's very close. Sometimes, the compounding continuous will be just a little bit more, but it's pretty close in this case. So for number 3, solving for x. So I need to make the exponents the same, or excuse me, make the bases the same. Goodness. So I rewrite 27 as 3 cubed. And so once the bases are the same, the exponents have to be the same, and so I can solve for x, and that is 2. So when I quickly check it, I put the 2 in up here. 2 plus 1 is 3. 3 cubed is 27. So I know my solution checks out. The next one, both the bases are the same, so I can make the exponents the same. Move the 24 over, so I have a trinomial. Factor the trinomial, so I get my factors set equal to 0, because we use that 0 product property. Then I can set this factor to 0, which means x equals -8, and this factor to 0, which means x equals 3. And so now I can check those two. Remember that anytime we get past a linear, we should be quickly doing a mental check to make sure our math is going to work and that this is a viable answer. And so when I check it, I get 24 equals 24, and I get 24 equals 24, so I know in fact that these two are my solutions. So remember, if you're using a calculator, the log button, LOG, is on there and ln. Those two buttons specifically use only those bases, and you find those on your calculator right here and right here. If you want the exponents that go along with log, log, which is base 10, you do second and log, and it's right above there. And on ln, if you want e to the x, you do second ln, and that gives you your e to the x on the calculator. There is an option now for entering things like this into the calculator. What the calculator is doing is using the change of base formula that we learned about last year, and so it's taking the base, the log of the argument divided by the log of the base. So this is log base 3 of 27, so it's taking log base 27 of log base 3. And so if you do that on your calculator, then the quickest way is alpha window, and the log is number 5, and then it gives you a template and lets you type it in. So then I can do 5 and go over here to 27, and that tells me that that's roughly what my answer is. Fraction, and you would say log of 27 and log of 5, and that would give you the same thing. And so this is how we've always done it in the past. So if you're on a calculator that doesn't have the new operating system, you're probably going to want to do that, and you would just say log base 27, close the parentheses, and then hit your division key, and then you could say log of 5, close your parentheses, and you would get the same thing. So there's 3 different ways that you could actually address that problem. So the log base 2, log base 2, section 3.2. I am just having a hard time today. Sorry about that. So we're looking at some problems to work out. Remember that you can solve for a base, you can solve for an argument, or you can solve for the output, which is the power. One way to do that is simply rewrite it. So I can say the base of the log is 2, the output of the log is the power, which is y. That equals 32. And then I know that I have 2 to the 5th power would give me 32, so y has to be 5. Log base 4 of 2, so that's the base of the log is 4, the base of the exponent is 4 to the output, which is y, and that equals 2. And so I know that since I'm getting a smaller amount, something has to be going on there. And I know that if I take the square root of 4, I get 2, and I know that the square root of 4 would mean that I had to have the exponent power of 1/2. So you're thinking square root of 4 equals 2, 4 to the 1/2 power equals 2. You can actually solve for any of this by just putting an unknown variable where you have a missing piece of information. In this case, what was missing was the exponent. So in this particular problem, log of the argument 1 over 100. So what is the log of the base? It's 10. So I can say 10 to the output, which is y, of the argument. And then I need to make these the same thing. This is a whole number base. This is a fraction. So I need to either change this to 1 over 10 to the y, so I can finish this out, or change 1 over 100 to a whole number with a negative base. And that's how I prefer to proceed. So I changed it to 100 to the negative 1. And I know that 100 is 10 to the power of 2, which means I have a power to a power, so I multiply the exponents and I get negative 2. And so if the bases are the same, then the exponents have to be the same. And so that means my answer is going to be y equals negative 2. All right, so now let's look at log of x. And so that's base 10, so that's log base 10 of x. And that is x equals 0. The y-intercept, there is none. The domain is 0 to infinity, and the range is negative infinity to infinity. So I get this graph that has this gradual curve out. And I use my parent function points that I learned last year, so 1, 0, and then 10 to the 1st power. That's just the inverse. So remember, if I do exponential, and remember how we talked about how we use 0 and 1 for those powers, once we get those points, which happen to be 0, 1, and 1, 10, I can use the fact that I know log or the inverse, and I can graph the point 1, 0, 10, 1. So these are the inverse points there, and that's how I get my graph. We already went over these log properties at the beginning, so we're going to use those now. For problem 3, we're going from log to exponential form. So how we change that, the base of the log is the base of the exponent, the output to the log is the power, and the argument is what the exponent equals. And isn't that true? If this was 16 to the 3/2, we would take the square root of 16, because that's what the bottom number tells us to do, and then we would raise that answer to the 3rd power, which does give us that 64. So in this case, the base of the log is 10, the exponent is -2, and the argument is 1 over 100. And if you think about what we did a minute ago, we just kind of went through this process, make this 100 to the -1, make this 10 squared to the -1, so I get 10 to the -2, which is what I'm working with here. If I'm in natural log, then my base is e, so I would say e to the output equals 10. Okay, so what it's saying is e raised to the power of 2.302, that's approximately 10. On 4 exponentials to logs, we reverse that process. So the base of the exponent becomes the base of the log. The output to the exponent becomes the power. And remember that the answer to a log problem is always an exponent. So wherever that exponent is, that's what it's equal to. So in this case, we would have log base 7 of the argument 149 equals the exponent, which is -2. And so finally down here, I have base of the exponent is e. So that means I have natural log because that's what base e is. And then I have y as my argument because that was the output, and the output to the log is the power. All right, number 5, we're looking at just working with some of the properties. So when I see this, remember the base of the log is 4, so I'd say 4 to the power of y equals 4. Well, that means y has to be 1. Or you can think about using that change of base. Log base 10 of 4 divided by log base 10 of 4 also gives you the output of 1. So you have a couple ways to reason through that one. This one, the base of the log is 2, so I write log base 2 of the output, which becomes the argument, and the exponent comes over to what your log equals. So if this is log base 2 and this is log base 2, then y has to equal 5. On this one, the base of my log is 2.3, so 2.3 to the y equals 1. And the only time you can get 1 as an output is if the power had been 0. On question 6, it's asking you to sketch, so let's quickly review how we sketch the graphs. We're going to find the domain, the x-intercepts, and the vertical asymptotes. So here is my log. What transformations do you see? We know it's base 3. That's not a transformation, but we know that this has shifted 4 units to the left. So that's my transformation. So then to graph this, I go back to the exponential form. That's the easiest, so you don't have to memorize a whole bunch of other points for logs. And so since this is base 3 log, then I make a base 3 exponent table. So using 0 and 1 again, I get 1 and 3, and I have a horizontal asymptote at 0. We know that log is the inverse to exponent, so that means the domain and range can trade places. So I switch my domain and range here, and the asymptote now goes from being horizontal to being an x equals, which is vertical. So here's my vertical asymptote graphed here after I have transformed the graph. So remember we said it was going to translate 4. Well, the vertical asymptote when I do the inverse is at 0, which is here, and then that vertical asymptote is going to go 4 to the left. And then that means once I calculate this, right, I will take my x values and I will subtract 4, because remember you're going in the opposite direction. So I would take 1 minus 4, 3 minus 4, and I get my new x values, and I plot my graph. So my graph looks like this. So the domain then starts at -4. We don't include it because that's the asymptote and goes to the right to infinity. The vertical asymptote is at -4, and the x-intercept then becomes at -3, 0. Okay? On B, so this is log of x minus 1 plus 4. The transformations are it shifts to the right 1 and vertically shifts up 4. So those are my transformations. It's base 10, so I use 10 to the x here and get my table with the horizontal asymptote at 0. So then I do the inverse, switch the domain and range for log base 10, and switch to a vertical asymptote at 0. Then I apply my transformation. So I'm going to add, I'm going to add 1, so that gives me my new x's. I'm going to add 4 to shift it up. That gives me my new y's. If it went 1 to the left, the vertical asymptote is now over at 1. So I have 1 vertical asymptote. I have the 2 points, and I have my curve that goes that way. So the domain is from 1 to infinity. The vertical asymptote is x equals 1. And the x-intercept, we'd probably have to use a calculator to find this because it's not going to intersect nicely, which is one of the downsides to log graphs and sometimes exponential graphs. They don't always have pretty numbers. So you're going to find that we're using a calculator a lot more in this unit than we do in others. And the last one, number 7, solving an equation. So we have natural log of x squared minus 3, natural log of 33. So if the log on this side equals the log on this side, then the arguments have to be equal as well. So we can move the 3 over, take the square root of both sides, remembering to include the plus or minus. And we can check it by making sure that when I plug my value in here, I should be able to be taking the log of 33. So all I'm checking is to make sure that comes to 33. And then again, we're using that rule with this side log equals this side log, then this argument has to equal that argument. So that's a quick review of all of the rules you learned about basic rules about exponentials, logs, and their graphs. And next time we'll start talking about working with them, solving equations, doing some other things, and using some of those formulas. Thanks, guys.